Welcome to the Deep Dive. We take complex topics, dive deep, and pull out the core insights you really need.
And today we're looking at an element that's, well, a bit of a paradox. It's fundamental to life, yet surprisingly scarce.
We're talking about carbon. Think about your morning, maybe coffee, toast, the clothes you put on, perhaps some medication.
Almost everything in that list, and certainly all living things, rely heavily on this one element, carbon.
Which is bizarre because, as you said, it's scarce. The sources we looked at point this out clearly, just 0.02% of the Earth's crust. Mostly things like coal, petroleum.
And even less in the air, carbon dioxide is only about 0.03% of the atmosphere. It's quite amazing, really. So that's our mission for this deep dive. How does this tiny fraction of an element become the backbone for millions, literally millions of different compounds? Way more than all the other elements put together. It comes down to some unique properties, starting with how it bonds. It sort of breaks the usual rules.
Okay, so let's compare. We know about common ionic compounds, right? Like sodium chloride, table salt. High melting points, high boiling points.
Exactly. And they conduct electricity when dissolved or molten. That's because electrons are transferred, creating charged ions with strong attractions.
But carbon compounds, totally different story. The data shows things like methane boiling way down at 111 Kelvin. Acetic acid is higher, 391 K, but still relatively low compared to ionic stuff.
Those low points tell you the forces between the molecules must be quite weak.
And crucially, they're poor electrical conductors.
Which strongly suggests no ions are being formed, so carbon isn't trading electrons like sodium and chlorine do.
So why not? What's stopping it? Takes us to the atom itself, doesn't it? Atomic number 6.
Yep, 6 protons, 6 electrons, 2 electrons in the inner shell, and 4 valence electrons in the outer shell. The magic number 4. To get that stable, noble gas configuration, like neon, it needs 8 valence electrons, so it's got a choice. Gain 4 or lose 4, but both are, well, practically impossible. Imagine gaining 4 electrons to make a C4 minus ion. The nucleus, with only 6 positive protons, just couldn't hold on to 10 negative electrons. The repulsion would be too great.
Okay, so gaining is out. What about losing 4? Forming a C4 plus ion.
That would take a colossal amount of energy, ripping 4 electrons away from that small atom. Extremely difficult.
So it can't easily gain, can't easily lose. It sounds like it's stuck.
But it finds a very elegant solution. Instead of trading, it shares.
Sharing. Right, forming pairs of electrons with other atoms.
Precisely. And that sharing of electron pairs is what we define as the covalent bond. Each shared pair counts towards the stability goal for both atoms involved.
So no ions, no strong electrostatic forces between molecules like in salt, hence the lower melting and boiling points. And no free ions means poor conductivity. Makes sense.
We see this sharing everywhere. Hydrogen atoms share 1 pair to form H2. Oxygen, with 6 valence electrons, needs 2 more, so it shares 2 pairs in O2, a double bond.
Nitrogen shares 3 pairs, right? A triple bond in N2.
Exactly. And carbon, needing 4, is tetravalent. It forms 4 covalent bonds. The simplest example, methane, CH4. 1 carbon shares its 4 valence electrons with 4 separate hydrogen atoms. Everyone's happy.
Okay, so covalent bonding explains why carbon compounds have those distinct properties. But that alone doesn't explain the sheer number of compounds. Millions of them. What's the secret to that?
Now we get to carbon's 2 real superpowers. These are the keys to its incredible versatility.
Superpower number 1.
Catenation. It's a fancy word, but it just means carbon's unique ability to bond with other carbon atoms.
Linking up with itself.
Yes. Forming long chains, branch chains, even complex rings like cyclohexane, C6H12. Think of it like Lego bricks clicking together in endless combinations.
And these carbon-carbon links, they must be strong, right? Because life needs stable molecules.
Very strong and very stable. That's a crucial point.
Huh.
Our sources mention silicon right below carbon in the periodic table. It can form chains with hydrogen, but only up to maybe 7 or 8 atoms long.
And they're highly reactive, apparently. Not exactly the basis for stable life.
Yeah.
That stability of the CC bond is paramount. Which brings us to the second superpower, tetravalency. Its ability to form 4 bonds.
Yes, combined with its small size. Having 4 hands means it can bond with lots of different atoms: hydrogen, oxygen, nitrogen, sulfur, chlorine, you name it. It's very sociable chemically.
And the small size matters
Because its nucleus can hold onto those shared electron pairs very tightly, very effectively. This results in strong, stable bonds, not just with other carbons, but with those other elements too. Larger atoms tend to form weaker bonds over the same distance.
So catenation builds the chains and rings, the basic skeleton, and tetravalency lets it decorate that skeleton strongly and stably with lots of other elements.
That's a great way to put it. And the way these carbon atoms arrange themselves can lead to radically different materials, even when it's only carbon atoms involved. We call these allotropes.
Ah, yes, like diamond and graphite. Mind-blowing that they're both pure carbon.
In diamond, each carbon atom is bonded to 4 others in a super-rigid tetrahedral 3D structure.
Resulting in the hardest natural substance known. And it doesn't conduct electricity.
Then you have graphite. Here, each carbon is bonded to only 3 others, forming flat hexagonal sheets, like layers of chicken wire.
And that structure makes it soft, slippery, think pencil lead, and, importantly, a good conductor of electricity.
That 4th electron in graphite isn't locked into a bond within the layer. It's sort of delocalized and can move between the layers, carrying charge.
And there are others too, right? The cage-like ones?
Fullerenes, yes. Carbon atoms arranged in spheres or tubes like Buckminster fullerene, C60, shaped like a soccer ball, named after the architect Buckminster Fuller. Amazing structures.
Okay, so arrangement matters, bonding matters. But even with the same number of atoms, say C4H10 butane, the structure can vary, leading to different properties.
Absolutely. That's the concept of isomers. Same molecular formula, different structural arrangement. Butane can be a straight chain or it can have a branch structure. They're different compounds with slightly different properties.
It just keeps getting more complex. Now, we've mentioned hydrocarbons, just carbon and hydrogen. You classify them based on the CC bonds.
That's right. You have saturated hydrocarbons, the alkanes, which only have single carbon bonds. Think methane, ethane, propane. They tend to be less reactive.
And unsaturated ones.
Those have double bonds called alkenes like ethene, C2H4, or triple bonds. The alkanes like ethane, C2H2, also known as acetylene. That double or triple bond makes them much more reactive.
Okay, so we have the carbon skeleton, maybe with some double or triple bonds.
Yeah.
But what gives compounds their really distinct chemical personalities? Like, what makes an alcohol an alcohol?
That's the role of functional groups. This happens when an atom other than carbon or hydrogen, we call it a heteroatom, like oxygen, nitrogen, or halogen, replaces one of the hydrogens on the carbon chain.
So it's like attaching a special tool or tag to the molecule.
Exactly. And that functional group dictates the compound's characteristic chemical properties pretty much regardless of how long the carbon chain is. Examples are the AOH group for alcohols, or the ALOH group for carboxylic acids, or CFO for ketones.
And this leads to families of compounds.
Yes, the homologous series. It's a series where you have the same functional group, but the length of the carbon chain increases progressively.
Like methanol, CH3OH, then ethanol, C2H5OH, then propanol, C3H7OH, all alcohols.
Precisely. Each member differs from the next by just one Nagios CH2 unit.
And what does that mean for their properties?
Well, physical properties like melting point and boiling point tend to increase gradually as the molecule gets bigger and heavier. But the chemical properties, largely determined by that functional group, remain very similar across the series. It allows chemists to study these vast numbers of compounds systematically. You can even write a general formula like CnH2n for alkenes.
Super useful. Okay, before we dig into specific examples, let's touch on probably the most common use of carbon compounds.
Fuel, undoubtedly. They're our primary source of energy through combustion.
And you can tell something about the combustion just by the flame color, can't you?
You certainly can. Saturated hydrocarbons, when burned with enough oxygen, like in a well-adjusted gas stove, give a clean blue flame. That indicates complete combustion, producing CO2 and water.
But sometimes you see a yellow flame, maybe smoky, leaving black soot on the bottom of your pan. What's happening there?
That's usually a sign of incomplete combustion. It often happens with unsaturated compounds, which tend to burn sooty anyway. But in a stove, it more likely means the air holes are blocked or not adjusted properly.
Not enough oxygen getting to the flame.
Right. So instead of just CO2, you get unburnt carbon particles, that's the soot, and also carbon monoxide, which is dangerous. So if your pots are getting blackened, check those air inlets. Good practical tip.
Okay.
Now let's spotlight 2 really important carbon compounds mentioned in the sources. Ethanol and ethanoic acid. Ethanol, CH3CH2OH, common name. Alcohol. Of course, it's the active ingredient in alcoholic beverages.
But it's also a really useful solvent, isn't it? Used in things like Tincture of iodine, cough syrups.
Yes, it dissolves many things that water doesn't, but the sources give a very serious warning here.
About purity.
Yes. While we consume diluted ethanol, ingesting even a small amount of pure ethanol, absolute alcohol, is lethal.
And then there's its cousin, methanol, CH3OH. Even worse, right?
Far worse. Methanol is extremely poisonous. The real danger is how the body processes it. In the liver, it gets oxidized to methanol.
And methanol is the real villain.
Absolutely. It reacts with the components inside our cells, causing proteins, the protoplasm, to coagulate. It basically cooks the cell from the inside, and it has a specific, terrible effect on the optic nerve.
Leading to blindness.
Permanent blindness, yes. That's why industrial alcohol often has methanol deliberately added to it. It's called denaturing. They usually add a blue dye, too, making it undrinkable and preventing misuse. A vital safety measure. Okay, shifting gears to the acidic side. Ethanoic acid, CH3COOH, better known as acetic acid.
And a dilute solution, maybe 5–8% in water. That's just household vinegar used for flavoring and preserving food.
That's the one. Pure ethanoic acid has an interesting property. It freezes at 290 Kelvin, which is about 17 degrees Celsius, not that cold.
So in cool weather, it can actually solidify.
Yes, forming ice-like crystals. That's why the pure form is often called glacial acetic acid. Chemically, it's classified as a weak acid.
Now, what happens if you mix these two, ethanol and ethanoic acid? Something quite pleasant, I hear.
Yes. If you react them together, usually with a bit of concentrated sulfuric acid acting as a catalyst.
And also to remove the water that forms.
Exactly. It helps push the reaction forward. What you get is an ester. Esters often have very characteristic pleasant smells, fruity or floral.
So that's where perfumes and artificial flavorings often get their scents from.
Many of them, yes. This reaction is called esterification, a lovely bit of chemistry, from fuels to flavors.
Okay, let's tackle one final everyday challenge where carbon chemistry comes to the rescue, getting rid of grime. The problem of cleaning, especially oily dirt. Oil and grease don't dissolve in water, so just rinsing doesn't work.
Enter soap. How does it work its magic?
It's all about the structure of the soap molecule. Typically, soaps are sodium or potassium salts of long-chain carboxylic acids. Think of them as having two distinct ends, a sort of dual personality.
One end likes water, the other likes oil. Precisely. You have the hydrophilic, water-loving end, which is the ionic part, the carboxylate group, COO+. And then you have the long carbon chain, which is hydrophobic, water-fearing.
So the carbon chain hates water, but is perfectly happy dissolving in oil or grease.
Exactly. So when you add soap to water containing oily dirt, something fascinating happens. The soap molecules arrange themselves into clusters called micelles.
How do they arrange?
The hydrophobic tails all point inwards, burying themselves in the oily dirt droplet they want to get away from the water.
And the hydrophilic heads.
They all point outwards, facing the water they love. So you end up with the oil droplet trapped in the center, completely surrounded by a sphere of soap molecules with their charged heads sticking out.
Like a little cage for the dirt.
A very effective cage. This structure, the micelle containing the dirt, forms an emulsion in the water. It stays suspended because all those negatively charged heads on the outside repel each other, preventing the droplets from clumping together.
So the dirt gets lifted off the surface, trapped in the micelle, suspended in the water.
And then it just gets washed away when you rinse. It's a remarkably clever mechanism.
But it doesn't always work perfectly, does it? What about hard water?
The bane of soap. Hard water contains dissolved mineral salts, particularly calcium and magnesium ions, Ca2+ and Mg2+.
And soap reacts badly with those.
Very badly. The ionic end of the soap molecule reacts with these calcium and magnesium ions to form an insoluble precipitate.
That horrible white, curdy stuff.
Exactly, what we call scum. It floats around, sticks to things, and crucially, it uses up the soap molecules, making the soap much less effective or even useless.
So we needed a better solution for hard water areas.
Which led to the development of detergents. These are chemically different. Often they're sodium salts of long alkyl sulfonic acids or similar structures. They still have the hydrophilic head and hydrophobic tail.
But the key difference is?
Their charged ends do not form insoluble precipitates with the calcium and magnesium ions in hard water. They stay dissolved and keep on working, forming micelles and cleaning effectively even in hard water.
That's why they're so common now in laundry powders, washing up liquid, shampoos.
Absolutely. They solved the hard water problem.
Wow. Okay, let's pull this all together. We started with this element, carbon, that's barely present in the Earth's crust or atmosphere.
Yet through its unique way of bonding, sharing electrons covalently because it can't easily gain or lose them, And its superpowers, catenation, linking to itself to form stable chains and rings, and tetravalency combined with small size, letting it form strong bonds with 4 other atoms, including diverse elements.
It becomes the foundation for literally millions of compounds. We saw how structure creates isomers and allotropes, how functional groups give chemical character, leading to families like alcohols and acids.
And how these properties translate into everyday applications, fuels, and their combustion, the crucial chemistry of ethanol and ethanoic acid, and the ingenious mechanism of soaps and detergents.
It really makes you appreciate the underlying chemistry when you wash your hands or cook a meal.
Ah.
It all comes back to carbon.
That simple CC bond unlocks staggering complexity.
Right, which leads to a fascinating final thought prompted by our sources. We mentioned silicon, carbon's neighbor in the periodic table. It tries catenation but fails. Its chains are short and reactive.
Unstable, yes.
So if building large, complex, stable molecules like DNA, proteins, the very machinery of life absolutely depends on that strong, reliable carbon bond. You have to wonder.
Was there ever really a choice?
Exactly. Was life on Earth almost chemically forced to be carbon-based? Simply because the alternatives, like silicon, were just too unstable, too volatile to support the kind of complex, long-lasting structures needed for life as we know it.
It shifts the perspective from carbon being chosen to perhaps being the only viable option that met the chemical requirements for existence on this planet. Something to think about.